Imagine a strip of paper. 3 cells, side by side, the numbers 1, 0, 1 written in them. Beside the strip, a small handwritten rule book, 8 rules, 20 lines. A pencil. That's the whole setup. Now the rule book is going to read those 3 numbers and decide whether they're a palindrome. And here's the strange thing. That setup, strip of paper, pencil, rule book, is a computer, not a metaphor for one. Literally a computer, in the most precise sense the word has. Stripped of every wire and chip and screen, this is what a computer actually is. Underneath. It was drawn on paper in 1936 by a 23-year-old British mathematician named Alan Turing, working at King's College, Cambridge. Electronic computers didn't exist yet. They wouldn't for another decade. Turing wasn't trying to invent the laptop. He was trying to settle an argument among logicians. The argument went like this. In 1928, the German mathematician David Hilbert had asked, "Is there an algorithm, a fixed set of rules, that can decide, for any mathematical statement at all, whether it's true or false?" It seemed answerable. Yes or no, Hilbert was betting yes. There was just one snag. To prove no algorithm exists, you have to know exactly what an algorithm is, precisely enough to talk about all possible algorithms at once. In 1928, nobody had that definition. Algorithm was a vibe. Useful, vague, completely useless for proofs. Turing's move was disarmingly simple. He didn't define algorithm from above. He watched what a person actually does when they're following a rule with pencil and paper, the most concrete kind of computing he could imagine, and he stripped it down to the bare bones. What is a person doing? They look at one little spot on the page. They keep a small amount of information in their head. They write a symbol, erase one, or move their attention to a nearby spot. They repeat. Everything else, insight, intuition, Turing set aside. From that, 4 parts. First, a tape, an infinitely long strip of paper divided into cells. Each cell holds one symbol, a 0, a 1, a letter, or it's blank. The tape is the machine's memory, and it's scratch paper at the same time. Second, a head, a reader-writer that sits over exactly one cell at a time. It can see what's in that cell. It can erase what's there and write a new symbol. It can move one cell to the left or one cell to the right. That's everything it can do. Third, a finite list of states. The machine is always in exactly one state, like a mood or a numbered step in a recipe. There are only ever a handful. 1 is the start state. Some are accept states or reject states. That's where the work ends. Fourth, the rule book. A table. Each row says the same kind of thing. If you're in state X, reading symbol Y, then write Z. Move left or right, and switch to state W. That's the program. No CPU, no memory chips. A tape, a head. States, a table. And the loop the machine runs is laughably simple. Read the symbol under the head. Look up the matching rule. Do what it says. Write, move, switch. Go again. Stop when you hit accept or reject. That is the entire engine of computation, according to Turing. Done. Now, here's the move that makes the whole thing radical. Turing claimed this pencil and paper toy captures every computation that has ever existed or ever will. Adding numbers, sorting a list, rendering Minecraft, running ChatGPT, all the same machine, different rule books. That sounds absurd. Let's check it. Back to our strip of paper. 1, 0, 1. The plan. Read the leftmost symbol, remember it, erase it. Walk to the rightmost symbol, check whether it matches. If it does, erase it and walk back. Repeat. If the tape goes empty, accept. If something mismatches, reject. Step 1. State start. The head is over the leftmost cell, reading a 1. The rulebook says, erase it, move right, switch to state, remembered a 1. The leftmost cell is now blank. The head sits over the middle cell. The machine is, in effect, holding a 1 in its head. State remembered a 1. The rulebook says, whatever you see, just keep walking right. The head walks past the middle 0, past the rightmost 1, into a blank cell. The rulebook fires again. When you hit blank, step back left and switch to state, check for a 1. State, check for a 1. The head is now over the rightmost cell. It reads a 1. Match. The rulebook says, erase it, walk left, switch to go home. The tape now reads blank, 0, blank. The machine walks left, hits a blank, and flips back to state, start. Now it does the whole thing again, this time with the 0 in the middle. Reads it, erases it, remembers a 0, walks right, hits blank, walks back, hits blank. The tape is empty. The rulebook says, empty tape, accept, done. The machine has decided. 101 is a palindrome. And nothing magic happened. 8 states and about 20 rules just performed real pattern recognition, comparing the front of an arbitrary string to its back. No algebra, no insight, no thinking. A tape, a head, and a table. That's what computation looks like at its absolute smallest. Now scale up. A normal Turing machine has its rulebook baked in. One machine adds. Another sorts. Another recognizes palindromes. Each is a separate device. Then Turing asked the question that changed the world. Could you build one Turing machine that takes the description of any other machine and simulates it? The answer was yes. He sketched it out in the same 1936 paper. He called it the Universal Turing Machine. One fixed rulebook that reads a description of any other machine off its tape and simulates it perfectly. A general-purpose computer, drawn on paper 10 years before any real one existed. And exactly that is your laptop. Your phone is not a separate device for browsers, games, and email. It's a single machine that reads program descriptions out of memory and simulates whatever they say. Every computer you've ever touched is a real-world version of Turing's 1936 sketch. Anything powerful enough to simulate a Turing machine is called Turing complete. Python is, JavaScript is, C is. Microsoft Excel with formulas, oddly enough, is. Conway's Game of Life is. The trading card game Magic the Gathering is. The bar for being a computer turns out to be remarkably low. But Turing didn't stop at this can compute anything. He used the same machine to prove the opposite in the same paper. There are problems no computer can ever solve. Not slow. Not unsolved. Impossible in the strict mathematical sense. The most famous one is called the halting problem. The halting problem asks, given a program and an input, is there an algorithm that always tells you in advance whether the program will eventually stop or run forever? Turing proved no such algorithm exists. Not for today's hardware, not for tomorrow's. Mathematically, ever. The wall is permanent, which is why bug detection tools can't be perfect. Why no antivirus catches everything. Why no compiler can fully verify your code is correct. These aren't engineering failures. They are direct consequences of a mathematical wall Turing drew in 1936, with 8 states and a strip of paper. And every modern AI lives inside those same walls. A neural network, in the end, is a very large rulebook running on a very long tape. It can be astonishing. It cannot be magical. It cannot solve the halting problem. The walls Turing identified in 1936 are walls for AI too, which is the strange gift of the Turing machine. To understand it is to understand, in one breath, what every computer in the world can do and what no computer ever will. A young man with a pencil drew the floor plan of a building we are still, 90 years later, living inside.